All right, welcome everyone to this session. Thanks for staying with us all the way until the end of the KubeCon. You are some of the brave souls who are remaining today for the last slot, so thank you. I am Vincent. I'm the CTO for Asia Pacific at Red Hat, based in Singapore. And I have with me Tamar.
Hi, so I'm Tamar. I'm from IBM Research. I'm an IBM Fellow and a Chief Scientist for Sustainable Computing.
All right, so what are we going to cover today? We'll start with a bit of introduction about Green AI, why it matters. We've talked a lot during KubeCon about optimizing AI systems, so effectively we are going to talk a lot about this, but really from the angle of energy efficiency. We'll talk about the key challenges and opportunities specific to cloud-native AI. And today we've made a choice to really focus on the optimization of AI inference, and we'll speak about why AI inference is so important, and then some of what's happening in the community right now and the possible next steps. So let's start by framing a bit the debate. We are actually at the very beginning of an AI sustainability crisis, but the challenge that we have in front of us is not new. So what I want to share is the explosion that you see today in AI demand essentially started as early as 2010 with the growing huge use of deep neural network technology, essentially. So since 2010, which is the deep learning era that you see pictured here, we've seen on average a growth of 4 to 5 times a year of the energy consumption to train models. So we are very much in a 15 years period already of this growth and this constant increase in number of resources used to train model. Not surprisingly, this has led to a huge surge in energy demand for data centers. And this is an interesting statistics that we expect by 2028, so we are just 3 years short of that. 19% of data center power demand will come from AI. So about almost 20% of it will be purely used for AI. As a result of this, we see the emergence of regulations to try to contain the use of energy. We are in Europe here, so you may be familiar with the EU AI Act, although it's actually for the European Union, but you are very close in UK. This is actually the first regulation globally that is going to mandate the disclosure of energy consumption for AI systems. That is probably the first of many regulations to come. I'm personally based in Asia Pacific, and I'm actually working with a number of government entities that are already elaborating their own regulations. So this is going to be probably a mandatory requirement for business to understand their consumption. Now, ironically, today, if you look at enterprise, and this is actually a statistics that was published by the State of AI Infrastructure last year, 74% of companies that use AI today are actually struggling to leverage their compute and acceleration infrastructure. So that means there are a lot of operational problems in optimizing the use of resources. However, it's not only a sad picture, because AI also helps us with a lot of improvements, and in particular in sustainability as well. I'm just sharing a few use cases here. They are very close to us because they are use cases that my friends at IBM Research have all contributed to in the climate science space. We've collaborated with NASA to take 250,000 terabytes of Earth observation data and build foundation model to basically read satellite imaging in a much more efficient way. We see result of about 4 times improvement in speed of interpretation of satellite imaging with this type of foundation model. So they allow us to do some prediction of extreme climate events, for example, and obviously this is a huge benefit to humanity. In material science, foundation models have been increasingly used to simulate and model new material structure, and that is a huge problem as well for humankind. I'll take the example of US. There's actually close to 800 substances that are toxic that are being monitored by EPA in consumer product. And there's hundreds of thousands of consumer products that now need to be retrofitted with kind of green and safe alternative. So that's a huge problem to solve. In environmental science, we have this problem with what we call these forever chemicals. Those are chemicals that take thousands of years to clear in the environment. And last year, actually, IBM Research had a partnership with the National Science Agency to look at the identification and remediation of this material. And last but not least, in health sciences, I would say AI has literally changed the game in terms of early detection of disease, particularly when applied to medical imaging. So those are just a few examples. So we definitely want to keep AI and make use of it, especially if it's not to generate funny pictures through a chatbot, but to actually, build real value with the application. And so we contend that in order to do this, we should be looking at the whole lifecycle and supply chain of AI and the system to actually improve from top to bottom. So there's a few ways of looking at it. Like the first way is through the machine learning lifecycle. A bit, when we discuss about security or DevOps and the shift left, actually I feel this applies to AI. When you look at the machine learning lifecycle from data preparation to feature engineering, model development, all the way to serving, the earlier you actually start to improve and simplify your flow, then the more results you have. So an example would be from a data perspective, if you can actually make more meaningful data set through data distillation, you could reduce your model training by up to 70% because you basically have to process less data. Yeah, then the whole life cycle is actually impacted by this because you have smaller model, faster testing, less resources used in the process. So we want to optimize through the machine learning lifecycle. And then the other angle is more in terms of pillars. We have a data optimization pillar. We have a model optimization. How do we make the model as small as possible? And then we have a system-centric pillar, which is more the efficient operation. So those are three levels, three types of a potential optimization we can do pretty much across the system. At the end of the day, we are trying to reduce the use of compute, accelerator, networking, and then storage. Now I'll come to why the focus of inference. Obviously, the whole life cycle is important, but inference actually has a very special place right now in terms of the overall consumption. I'm actually using some figures published publicly by Facebook AI, and they are interesting in the sense that I'm going to say for some of you who are enterprise here, whatever you see here published from Facebook, you are probably way higher than this in terms of the place of inference in your consumption. I mean, let's be reminded that Facebook really has a business based on data, and they actually tend to retrain and retune their model on a very frequent basis. Most of you and us in the audience who actually use more classical use case of data, we tend not to do this on such a frequent basis. Yeah? But so Facebook published this study, and it's very easy for them to actually measure where the different part of the life cycle and their contribution, because they have specialized fleet of hardware and infrastructure dealing with the different part of the processing. So in their infrastructure, data and model tuning and inference are literally different fleet of servers and different type of optimization. So what they actually showed is close to 65% of an AI system operational carbon footprint actually is spent on inference. Operational means the energy spent to basically run the inference of the model. So that's almost, it's around 2/3 of pretty much the overall total. At the same time, we also demonstrated that optimizing the platform level, so that's the operation, can lead to as much as 800 times improvement in consumption. So that's like a huge reduction if you actually take care of optimizing your inference. you can get fantastic results. And let's not forget something to finish on this topic. A big part of the carbon consumption of AI is also actually embodied in the hardware. So when, for example, you buy a 2 cluster of H200, when you actually effectively only using one, obviously you actually have a lot of embodied carbon in the process, which is coming from the manufacturing of the hardware, the shipping, and so on. So the other interesting aspect is 50% of the embodied carbon comes from the hardware manufacturing. So when you optimize in France, you basically need less hardware, and you are also getting a 50% reduction in overall carbon. So that is super interesting. So that's what I wanted to share really on explaining why we have this focus on efficient inference. And I'll let Tamar now explain some of the work we are doing in this space.
All right. Okay. So my first statement here is that green AI is efficient AI. And why is that? When you work on your efficiency, you save resources. If you use less resources, by definition, you use less energy. Energy is a resource, so you can also think about it like this. So it's all about running your work, meeting your SLOs, respecting your SLOs, while making the best use of resources, using less resources, and using them more efficiently. Now, there are lots of different techniques for efficient AI across the life cycle, and I'm going to mention a few of them. So you see on the purple boxes there are techniques that have to do with model architecture. So this is the AI scientist who is working on new architectures such as LoRa adapters. With LoRa adapters, you freeze some of the weights when you're doing fine-tuning for particular tasks, and then you get these adapters that are just being used for that particular task. Basically, breaking the monolith. Mixtures of experts, that's another model architectural principle that can help us have more efficient inference and more efficient fine-tuning. Quantization, that's another thing. Speculative decoding, this is a runtime inference technique where you are guessing ahead of time, like optimistically, a number of tokens together using a smaller model. These are all techniques which are used in order to optimize a single model. Okay, now, the second category is what you see with the blue rectangles. Here, we're talking about what's going on in deployment and operations. Completely different story. So what's going on there is that you have multiple different models that are serving multiple different users. These models have very different characteristics, and the requests are also could be of very different nature. Some of them are latency bound, some of them are more about throughput, okay? And all of this is running on a cluster with heterogeneous hardware. Heterogeneous hardware is really important, and I will tell you why. We believe in fit-for-purpose accelerators. You don't want to run your entire workload on GPUs because you're going to waste a lot of cost and a lot of energy. So if you have a large model in your training and you have a training job, obviously you want to use GPUs. If you have inference requests or if you have smaller models, then you may be better off with other types of accelerators. Okay. So this is really the role of the platform. The role of the platform is to bridge between the models and the different jobs and requests and the infrastructure that is a heterogeneous infrastructure with fit-for-purpose accelerators, and to do that in the most effective way. All right, so going a little bit into the challenges of that platform. So you really want to you have really multiple different patterns that are emerging in that landscape of AI. Support chat box, so you have low latency. This is where you go to the bank and you can't find, where can I find my BIC number or something like that. and you're chatting with an AI chatbot, and you can be tolerant because you're used to getting support from people, and people are really slow, so you can be tolerant, but you still want low latency. Okay. So then you go to code assist. Code assist is like you're coding and you want auto-completion, for example. Here, you also want low latency, but you want much lower latency, because if it's not fast enough, you're going to complete the code yourself, right? Developers have no patience, we know that. And the context window here is much bigger, because you need to understand the entire code base in order to help you, the AI needs to understand the entire code base in order to help you debug, do autocomplete, and so on. Then you have an LLM service. Here, we're talking about high volume, multiple tenants, lots of interactive requests, all coming together, and you need to support that. Document processing, completely different idea. Here, it's about throughput. Document processing is all about throughput. LLM-powered search, this is a hybrid, real-time LLM and RAG, which is transactional database kind of workload. And agentic, completely different story, where you now need to worry about the end-to-end latency, the context across all of these transactions, topology awareness, and so on. So all of these are different patterns. And what you see on the right is you see a bunch of metrics. Throughput, which is token per second, time to first token, time between tokens, blah, 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 all these metrics. And you see some selected strategies. There are lots of different strategies. The point here is for each one of these patterns, you're going to need other strategies. For chatbots, you need sticky management, for example. For code assist, you want context truncation. So you want to eliminate the code that is not important and keep the code that is important in order to reduce the context. For LLM service, you need SLO-based routing and queuing, because you're going to have requests with different SLOs, and so on and so forth. So really, the variation in context length, degree of similarity across queries, latency and throughput trade-offs, and so on, will affect the strategy that you want to use. And that's what makes it so complicated. So really, just to summarize, this is a summary chart which says, look, based on the use case, you may want to use different techniques in order to achieve your goals. And your high-level goals at the end of the day is, like I'm showing here 30% reduction, but maybe it's more, a significant reduction or a significant increase in your effective throughput, which is a successfully processed token. Sometimes we call it good put, a significant reduction of cost, reduction of energy, and while still maintaining user perceived latency and so on. That's what you want at the end of the day. The challenge here is how to match the patterns that you have with the strategy that you use. So this is where the platform comes into play. The goal is to maximize the overall output while meeting your SLOs and minimizing your cost, bridging between these heterogeneous LLMs and adapters and this heterogeneous infrastructure with fit-for-purpose accelerators. And how do you do that? So you need to integrate best-of-breed optimization techniques in a coherent fashion. And what I mean by coherent fashion is that you want all of these optimization techniques to work with each other rather than against each other. And this is very important. So you're going to see that lots of techniques are being introduced. This area is evolving really, really quickly. So we're going to go quickly through some of them. Right-sizing and GPU slicing. Why do you want to do GPU slicing? Of course, you want smaller LLM models to use just a slice of a GPU. They don't need the entire thing. So you want to share GPUs across models. You can use MIC partitions or MPS. And you will need right-sizing techniques. What is right-sizing techniques? Is techniques that allow you either through profiling or by analytic methods to assess the size of the slice that you need for a particular model. And by the way, I'm mentioning here under sources, you're going to see the links to some work that we did in IBM research in collaboration with Red Hat and NVIDIA on InstaSlice, which is an open source project that allows you to dynamically slice GPUs. And there is another work that we did here that is really showing you how to right size. When you combine the two, then you can get really, really good results and save a lot of energy and a lot of cost. So then we go to the other one, routing and queuing. Why do you need routing and queuing? Why is it not just load balancing, the good old load balancing? Well, that's because you have different requests with very different nature. Batch versus interactive, right? And it's very unpredictable to know how long it's going to take to process a single request. Why? Because you don't know how many tokens are going to be generated. So you need intelligent load balancing and intelligent queue management. You want to avoid the head of the line problem where one request is blocking everything else. You want to potentially introduce eviction and techniques like that. You may want to reorder the queue, or even the way you arrange the queues matter. So we did some work in collaboration with UIUC. So this is IBM Research and UIUC. Very interesting work. I recommend to read this paper because it's going into all these policies and a lot of work that already went into the VLLM open source project. All right, so the point here is that these things depend on one another. So as you do routing and queuing, you also want to do caching. So one of the most important things here is that when you KV cache management is a very important technique that is being used. And this is because of the autoregressive nature of LLMs. So you want to reuse, it works in iterations, and every iteration generates the next token. But what you want is you don't want to recompute everything again and again. That's why you use KV cache. However, in your load balancing or in your routing, you better do it based on where the cache is, right? Otherwise, you're going to get suboptimal results. So you see that there's some interdependencies that are starting to appear here. So we talked about caching and loading and why you need them, right? Autoregressive nature. That by itself is a very complicated problem because not only that you need a KV cache in every node, it's also how do you share KV cache across nodes, because you're not always going to be able to send all of the prompts that are that relate to the same user or to the same session or that are similar to the same node because of load balancing issues. Okay, so you need to share the KV cache across nodes. How do you do that? Lots of ideas. Project Mooncake is a good example that is really, really sort of stretching the possible here and looking at techniques such as disaggregated prefill and decoding and so on. And then LoRa management. So remember that we discussed the LoRa adapters. That's another thing here. We can have thousands of adapters, and these adapters could be dynamic. So where do we cache each adapter so that it's going to be available for the requests that need it? Because not all requests are equal. They're going to need different adapters. And then how do routing and queuing actually factor it in the decision making? All right, so here we created another dependency. And then finally, auto-scaling. Auto-scaling is all about the number of VLLM instances. So you have a model which is running on 3 or 5 VLLM instances, and you need to grow the number of VLLM instances based on your load and shrink it based on your load. In that process, you also need to make placement decisions. So where am I starting that new VLLM instance? That also depends on all of these other elements. So one thing is you want to look at the size of the queue in order to know how many instances you need for a VLLM request. And the other thing is you need to understand what is cached where in order to place the new VLLM server for a particular model in the optimal place. So we're introducing all of these interdependencies, and I think that this is more than just dependencies. Dependencies is like when you need a library in order to run something, and it's easy to handle. I call it intersectionality. Intersectionality in the sense that there needs to be some sort of a very intelligent awareness so that these control mechanisms are going to work together so that 1 + 1 is going to equal 3, not -1. So the question is how to keep the balance. On one way, we see a huge, like a light speed evolution of the technology, And I bet you probably in 1 month I'm going to have another pink box here because there is going to be a new technique. But I can bet you 100% that there are going to be more algorithms to do better distributed cache management and so on, and better routing and better queuing and so on. So the area evolves really quickly, and we really want to maximize the combined outcome of these that we're getting from all of these optimization techniques, right? So how do we do that? So these are some architectural principles. First of all, modularity and separation of concerns. We really have to have well-defined APIs, well-defined control flow and data flow. What does the routing need to know about caching so that the routing could be optimal, right? And we really want data-driven optimization. So we need benchmarking tools that allows us to understand what are the benefits that we're going to get from particular techniques, but also when we combine techniques together, right? We want to leverage best-of-breed open-source technologies, and we want to support this rapid evolution, working together as a community so that we can test new algorithms quickly. So if I'm using my favorite router, but I have a new distributed KV cache algorithm, I can test the two together, and I don't need to reinvent the wheel every time that a new technology comes into play. And obviously support heterogeneity, because that's also good for efficiency and for cost reduction. So now I'm going to pass it back to Vincent to talk about the role of the CNCF in supporting the community effort around this architecture and around this technology.
All right, so we've seen extremely complex problem to actually solve the platform efficiency problem. And actually that opens really an avenue for the CNCF to really help the industry to look at how we standardize some of these practices and efforts. So you probably have heard this morning during one of the keynote examples such as the Gateway API extension for LLM inference. This is an example of standard that the CNCF as a group can promote for technology vendors and users to really standardize the way they are going to look at optimizing inference to model. You may have heard as well in the telco session about a project called Kepler. Kepler essentially is a standard for energy observability in workload, and obviously we are using it to evaluate the energy spend of AI workload in a cloud-native context. So the CNCF has this huge role to play to help us actually standardize our technology contribution to some of the platform capability. Now, the challenge though is having technology and standard is good, but it's actually usually difficult for any player to build a consistent platform. So what we started about a year ago is a joint partnership between the CNCF AI work group as well as the TAG Environmental Sustainability to look at best practices of architecting sustainable platform. So we started to write a white paper, and this white paper essentially is looking at 4 dimensions which influence the approach to sustainable AI, which is the type of deployment environment that you are actually deploying the technology on. It could be anything from a public cloud footprint to an edge computing footprint. It looks like the type of AI system. Tamar has explained earlier that this literally drives the type of optimization you can leverage. Obviously, the AI lifecycle. Are you optimizing the data, the model, the operation? And then, of course, the persona. So who is actually operating the platform and can take active steps to optimize. So this white paper is meant to provide a collection of best practices in building and operating sustainable AI platform. And so I'll finish with this. If this topic is of interest, I would invite you to find out more about the work by the Cloud Native AI Working Group, which I'm part of. We did a lot with AI in general, but as you've probably inferred from your time in the past 3 days at KubeCon, a lot of the focus right now is operating AI efficiently. The second link is really on the working group on the Sustainable AI white paper. And so we are very close to publish an open draft for consultation. But right now you can find about 10 to 15 different best practices and techniques already in the white paper that are shared across different organizations. And we very much welcome more technical contribution or reviews. Thank you very much for your attention and have a great weekend ahead.